Good afternoon and welcome everyone to this week's edition of the joint astronomical colloquium here in Heidelberg. It is with great pleasure to welcome Anastasia Fialkov from Cambridge, UK, who will talk about 21 centimeter cosmology, about the different observational theoretical means to evaluate what we know about cosmic dawn and how we approach the question to learn more about this interesting phase of cosmic evolution. Let me say a few words about the speaker. She studied in Israel, in Tel Aviv. She did then a postdoc at the École Normale in Paris. From that, she moved to another Cambridge, to Boston, to Harvard. And since half a year, she moved to the UK, Cambridge, to the Institute of Astronomy. And she will very soon take a faculty position at the University of Sussex in Brighton. In between, she has made several extended visits in Tokyo, in Caltech and many other places. He has received many distinguished fellowships, and she's well known for her work, for her predictions of 21 centimeter cosmology and the related physics. And this is what she will be talking about today. So let's welcome Anastasia.
Thank you. Thank you, Ralph. Unfortunately, Sussex is not a faculty position yet. It's a Royal Society fellowship, which is nice. And I'll be talking to you about cosmic dawn and how can we probe it with 21 centimeter signal. This is an outline of my talk. I will first introduce what 21 centimeter line is, and I hope we will be all on one page and you will understand what I'm presenting here about measurements and the constraints on cosmic dawn that we have. So 21 centimeter signal in a nutshell is an emission of neutral hydrogen. We know that the lowest energy level of hydrogen atom is split because of the interactions of spins of proton and electron. And when an atom undergoes this transition, a photon of 1.42 gigahertz is emitted or absorbed. And the wavelength of this transition is 21 centimeters, and that's what gives the expected signature of cosmic dawn, dark ages, and reionization. So we'll be talking about how we model this signal from redshifts around 20, how it depends on astrophysics, and what are the current observational status on this signal. Maybe some of you know that earlier this year, in February, we actually had the first claim for detection of this line. Here you see an absorption of cosmic microwave background in neutral hydrogen. This is still to be confirmed. It's a very controversial signature. I will talk to you about why it is controversial and what the community, what are the steps that community takes nowadays to confirm or disprove the signal. And I also show you some constraints that we made using our models and the existing data on high redshift astrophysical parameters. So I'll start with the introduction and observational status. So this is an evolutional history of the universe. It's just a cartoon taken from the publication by Avi Loeb in 2006. And here we see all the stages of the evolution through which the universe underwent after the release of cosmic microwave background radiation at redshift of 1080. Which corresponds to the cosmic time of 380,000 years. And as we see on this plot, fluctuations that initially were tiny, around 10 to the minus 5 contrast compared to the mean density of matter. These fluctuations first grew linearly, forming a structure in dark matter, and after baryons decoupled from cosmic microwave background, they started infalling into the dark matter potential wells. So right after decoupling of cosmic microwave background, that was the only light that existed in the universe. and the universe otherwise was dark and empty. As I said, fluctuations grew first linearly and then non-linearly in dark matter, forming big enough potential wells in which gas eventually was able to fall in, forming first stars ever in the history of the universe. Analytical calculations show that these stars form roughly when the universe was very young, around 400 million years old. And they were originally very rare because you really need to create special conditions to form the stars. The overdense, you need a very strongly overdense region, highly biased region, and these were very rare at early times. So on this plot, you see that first times form are very dispersed around the sky. There are only few star-forming regions at high redshifts. The epoch when first stars form is referred to cosmic dawn, and the star formation has feedback on the universe. So we know that after cosmic microwave background decoupling, the universe was expanding, it was empty, and the gas was cooling down with the expansion of the universe. And the formation of first stars had the effect by heating and reionizing the gas. So on this plot, every gray bubble around the star-forming region is actually a bubble of ionized gas. So you see that these patches are very local at the beginning. And around every bubble of ionized gas, I can draw a bigger bubble of heated gas because X-rays had a larger mean free path, so they would travel larger distances before they output their energy. So star formation would reheat and reionize the gas. And as the universe evolves, there are more and more regions where stars can form, and bigger galaxies are assembled. So eventually we come to the epoch when the galaxies are massive and their radiation reheats and reionizes the gas in the intergalactic medium. So this epoch is referred to as epoch of reionization, and it happens around redshift of 6. And today, of course, the intergalactic medium is very hot and fully ionized, with few neutral regions remaining inside galaxies. So there are a few crucial events that happened during cosmic dawn that we have never actually observed because our observations are limited, and this includes formation of the very first stars and black holes. If I put the existing observations in the context of this picture, we have observations of cosmic microwave background by Planck and Bicep Keck array and other experiments. And we have a lot of observations of low redshift universe starting from our own solar system with sun and planets going to extrasolar systems and further galaxies such as Andromeda and all the cosmic web that we observe with large-scale structure surveys. And pushing the observational frontier even further, we observe high-redshift quasars and galaxies. So the highest redshift quasar is located to the redshift 7.54. And the galaxy at the highest observable redshift is at 11.1, detected with HHT using a cluster as gravitational lens. So these are very rare objects that they are very bright, but they start probing the epoch of reionization and the end of cosmic dawn. However, this area here is still unexplored. And just to remind you that all the intergalactic medium here located between the gray spots is still neutral and much colder than the CMB during most of the evolution of the universe. So in principle, all this gas here is mainly neutral hydrogen, 74% by mass, and this gives us the hope to probe it through the 21 centimeter signal. So the first detection that was claimed just a few months ago is exactly this attempt to probe the intergalactic medium through the absorption of neutral hydrogen, and it would be the first ever observation from that epoch, probing the onset of formation of first stars, the formation of first X-ray heating sources such as X-ray binaries, and the epoch of reionization, the beginning of epoch of reionization. However, we still don't know if this signal is true or not. So this signal, I will talk about it more at the end of my talk, was detected by this very simple antenna. It's just a meter across here. It's located in Australia in a very radio-quiet zone, and you see the dimension compared to the bushes in Australia. This mesh on the ground is very functional. It reflects radio waves and protects the instrument from interference with the reflections from the ground. And as I said, if the signal is real, it would tell us the history of star formation at early times. So according to the signal, first stars form around when the universe was around 200 million years old, at redshift around 22. Going back to the basics, so my signal is 21 centimeter signal produced by neutral hydrogen atoms, and the early universe was 74% by mass composed of neutral hydrogen, so there are many atoms in the intergalactic medium here that produce the signal. An individual atom emits the signal. So the rate is 10 to the minus 15 per second. It's a forbidden transition. It doesn't happen in the lab, but the volume of the universe is huge, and eventually the signal is observable. Our instruments becoming better and better and are able to probe the signal. The crucial quantity that I will be discussing is the spin temperature, which parameterizes the transition of this transition. Basically, it tells us the rate of the transition from the excited level when spins of proton and electron are parallel to the lowest energy level when they are anti-parallel. And the effective energy of this transition is tiny, it's 5.87 10 to the minus 6 electron volts. So it's tiny compared to all other transitions of neutral hydrogen. And again, this transition would be emitted from everywhere where we have neutral hydrogens outside of ionized bubbles during the epoch of reionization. This line, the intensity that we would observe, this line, it's actually very tightly related to the astrophysical processes that take place at high redshifts. In particular, there are three crucial processes. Scattering with CMB would drive this line to the equilibrium with the CMB, so if we wait long enough, the spin temperature would be equal to the temperature of the CMB. If the gas is dense enough, then interatomic collisions would drive this effective temperature to the kinetic temperature of the gas, which is set by thermal motion of hydrogen atoms. And then there is a very important effect which is called Wolfshausen field effect. In the presence of external Lyman alpha radiation, the atom can absorb Lyman alpha photon, go to the n equal to 2 excited level, and then re-emit it. And eventually the atom can end up in a different state of this 21 centimeter transition than the original state. Therefore, in the presence of Lyman alpha radiation, the spin temperature is driven to the color temperature of the radiation, actually, which is very close to the kinetic temperature of the gas. And that's actually why we would see absorption at early times. And overall, you can parameterize the spin temperature in terms of temperature of the CMB, kinetic gas temperature, and the effective coupling, the collisional coupling and Lyman alpha coupling, which is very close to 1 in the presence of Lyman alpha radiation. Are there any questions about these basic processes? So this tells us that the expected intensity is very closely tied to astrophysical processes, the process of heating or how the gas temperature evolves, process of star formation through the intensity of Lyman alpha background, and it also is tied to cosmology through these collisions and fluctuations in all these quantities. So if I write the observable temperature, what we actually observe is the differential when we subtract the CMB temperature, which serves us as a background radiation. We would see that the signal is mainly driven by the neutral fraction, so amount of neutral hydrogen atoms that exist in the universe. And to the large extent, I can depict it as a Swiss cheese model. There are holes carved by ionizing radiation, and the otherwise neutral gas produces the signal. And then there is a term that you can derive from radiative transfer equations, which tells us that the signal is proportional to 1 minus the ratio of radiative background temperature, which for us is the CMB, divided by the spin temperature of the 21 centimeter transition. And then there is a bunch of cosmological factors. So this term is very closely related to the heating history and the temperature of the gas. So as I explained before, spin temperature is very close to the kinetic temperature set by collisions between atoms and also Lyman alpha radiation. So therefore we can use this line as actually a cosmic thermometer, and it would tell us how hot or cold gas is compared to the cosmic microwave background radiation. On this plot you see the mean gas temperature versus redshift. This dashed line is the temperature of the CMB radiation. Dotted line is the temperature of the gas. As we know, the CMB cools down as 1 plus redshift, and the gas in an adiabatically expanding volume cools down faster with 1 plus z squared. So this is the temperature of the gas. And the solid line shows the spin temperature. It first follows the temperature of the gas coupled by the collisional coupling. And then when collisional coupling becomes inefficient, it decouples and goes to the temperature of the CMB. So at this point, we would not see the signal because this term would be equal to 1, and the signal vanishes when there is an equilibrium with the CMB radiation. As I will tell you in a second, when stars form, they produce Lyman alpha radiation and couple the temperature, this spin temperature to the temperature of the gas again, and then they drive the heating process. So we would expect to see the spin temperature dipping again and then going up. So that's how we can use 21 centimeters cosmic thermometer, but we can also use it to characterize cosmology, follow growth of structure in this new redshift range, which is between 6 to 60 or even higher. So it is a complementary probe to the CMB and the large-scale structure surveys. And I'm not talking about this, but if you're curious, you can ask me later. This signal is also sensitive to the effects of dark matter, such as dark matter annihilation or decay, or maybe warm dark matter scenarios. It's very sensitive. It's a very sensitive probe of structure formation and heating and ionization. So if once we have cosmological information, we will be able to also put constraints on properties of dark matter and the cosmological. Use it as a cosmological probe. So in average, if we average the signal around the sky, and we can do it at every redshift separately because of the expansion of the universe, the intrinsic wavelength, 21 centimeter, is expanded, or frequency goes down, as 1 plus redshift. So we can plot a spectrum as a function of frequency, and in a generic scenario, it would look like that. There is a signature that you don't see here from the epoch when there were no stars yet, and it depends on the atomic properties of the gas. And then, as I showed you before, that because of the coupling to the CMB, the signal nearly vanishes until star formation produces Lyman alpha photons in large quantities. Lyman alpha photons couple the spin temperature to the temperature of the gas, and we see it in absorption. And then eventually X-ray, it would go even lower, but X-ray heating starts, and the gas temperature is heated by X-ray binaries, so whatever are the source of X-ray photons, to the temperature above the CMB level. So we start seeing this differential signal in emission. And then eventually reionization starts being important and the signal vanishes completely. So it's this dip that EDGES team claims to detect at redshift around 17. As I said, we still don't know if the detection is real. However, as with the CMB, we know that the universe is not homogeneous. There are fluctuations on small and large scales, and there is structure formation. So same with 21 centimeter signal, it would fluctuate at a given redshift. So the signal is seen in emission or absorption. depending on the astrophysical processes locally. And it is also driven by large-scale processes such as velocities between dark matter and gas, which fluctuate on a scale of 100 moving megaparsecs. So there are many sources of fluctuations that one needs to take into account when modeling the signal. In particular, as I showed you, star formation was patchy at the beginning, and therefore radiative backgrounds produced by stars also fluctuated. X-rays were produced locally, but they propagated far into the intergalactic medium, heating the gas, but this heating was non-homogeneous, and then it imprints fluctuations in gas temperature and also 21 centimeter signal. And other sources of fluctuations include Lyman-alpha radiation, Lyman-Warner radiation, and ionizing background, and of course the initial density field. So I will show you in a bit a particular example of what we expect to see from a fluctuation in X-ray sources, and in particular even particular properties of X-ray sources such as spectral energy distribution or typical energy produced by X-ray sources affects the signal strongly. For example, if we take hard sources with a typical mean free path of a few hundred megaparsecs compared to soft sources with a typical mean free path of much shorter scales, we see a strong impact on the overall gas temperature. Fluctuations in gas temperature are much milder and on larger scales when photons are hard, while in the case of soft sources, they are very strong, but on much smaller scales. This is just an effect of typical scale, and it's imprinted in the 21 centimeter signal. So in addition to this global signature, we can study fluctuations at every redshift. And just like in the CMB radiation, we can plot a power spectrum at every given redshift. However, we will have a 3D information and tomographic scan of the universe, right? So in principle, I should show you a three-dimensional power spectrum, but what is useful to show is actually an evolution of power at a given co-moving angular scale. So fixing an angular scale and just following the evolution of power at this scale. And then, as in the global signal, where we see the structure of peaks and troughs, also in the power spectrum, we see fluctuations, and we see peaks and troughs, and every peak here can be attributed to a different source of fluctuations, properties of the source, and distribution of the sources around the sky. In particular, at higher redshifts, we see the peak contributed by non-homogeneous Lyman-alpha radiation produced by first stars. Then there is a peak imprinted by non-uniform heating from X-ray sources, and then there is a peak from reionization. So just imagine having all this information, and from it we will know how the universe evolved, what was the sequence of cosmic events, when first stars formed, when first X-ray binaries formed, how common were the sources, and what were the spectral properties of the sources, just from these signals. And of course, with the 21 centimeter, we will have also the full 3D cubes. We can study high order statistics and do imaging and do other stuff eventually. So here I showed you a typical example where I had to assume some particular sequence of astrophysical events, but in reality we actually don't know what happens there. We don't have any observations except for the EDGES law claimed detection. So if you vary astrophysical parameters in the wide range allowed by other than EDGES observations, we end up with a scatter in predictions. Every blue line here is a valid astrophysical scenario. On your right-hand side, you see a global 21 centimeter signal. On the left side is the power spectrum at a co-moving angular scale of 1/10 of inverse megaparsec. And we see that fluctuations have an uncertainty of 4 orders of magnitude, and the global signal also populates the entire space of brightness, temperature versus frequency diagram. So there is just a large uncertainty in our modeling of high redshift universe. And here I included variation in star formation and the strength of X-ray heating sources, and also properties of ionizing sources, all within the allowed ranges. Just a side mark, all these fluctuations would be observable by the square kilometer array, so sensitivity curve would follow something like that. So even in the worst case scenario, SK will be able to measure these fluctuations. And naturally, because both global signal and power spectrum come from the same astrophysical scenario, there is a correspondence between features of the global signal and features of the power spectrum. And this can be used for signal verification. For example, comparing where this absorption feature falls in and where the X-ray peak shows up in the power spectrum could let us check the consistency of the experiments and the detections. So I'd like to show you a particular example of how an astrophysical property affects this signal, and I want to focus on X-ray heating sources, which drive the temperature of the gas from very low values of a few Kelvin to the temperature above the CMB, few hundred kelvins up to 1,000. There are many sources discussed in literature. We still don't know what dominated cosmic heating. The leading candidates are X-ray binaries, which probably existed in large quantities, formed from the first massive stars. However, people are also discussing thermal emission from hot gas in galaxies, heating by AGN or first mini quasars. Also discussed are dark matter annihilation, cosmic rays, magnetic fields. And for X-rays, the important properties are the luminosity of the population, spectral energy distribution, and also growth of population in time. All those properties affect the signal and can be constrained from the signal in future. Here I will show you an example of spectral energy distribution. So this figure shows the spectral energy distribution as a function of the wavelength of produced photons. People are often using this soft power law spectrum, for example, to model emission of hot gas in galaxies. And I'll compare it to a realistic case of X-ray binaries. So X-ray binaries are from stellar black holes, and the spectrum peaks at around 1 keV. So these photons are much harder than emitted by thermal gas in galaxies. We don't know how efficient these populations were compared to present-day X-ray binaries, and therefore there is just a parameter that parameterizes their luminosity. I will show you an example where the normalization of these two spectra is the same, and the only difference is the typical energy of X-ray photons. So 0.1 keV compared to 1 keV. And as I mentioned before, the main difference is the mean free path of these photons. So hard photons have much smaller scattering cross sections, and they can propagate to larger cosmological distances than soft photons. Therefore, the energy from source is distributed on much larger scales, and also the universe actually expands between the time when the photons were produced and the time when they were absorbed. So overall, heating is way less efficient in this case. In the case of soft sources, most of the energy is immediately injected in the gas. So earlier I showed you how the gas temperature would look like for these two scenarios, and here I show you the differential brightness temperature with the CMB as the background source. So in the case of hard photons, we see a very diffused fluctuations on large scales, and overall the gas is much cooler than in the case of soft sources, where fluctuations are on much smaller scales and of larger amplitude. So just changing the spectral energy distribution of these photons, this is the effect that we have on the global signal, so around 40% deeper absorption feature and shallower emission feature, just because the universe has more time to cool down in the case of hard sources. So solid line here is the case of X-ray binaries, and dashed line is the case of soft sources. However, the more important information is in the power spectrum. In particular, here on the left-hand side is the case of soft sources, and right-hand side is hard X-ray binaries. So we see that this heating peak that is imprinted by fluctuations in gas temperature is simply not present in the case of X-ray binaries on this scale, and this is because this particular scale, 0.1 inverse megaparsecs, is smaller than the mean free path of this photon. So that the fluctuations are smoothed out, erased on these scales, and we don't see these fluctuations in the 21 centimeter signal, while they are very well resolved in the case of soft sources. So if SK measures this peak, we will, at this particular angular scale, we will know that we can relate the presence of the peak to the mean free path of X-ray sources and find out what were the dominant heating mechanisms at high redshifts. So this is again around redshift 25 or 15, but it's very model dependent, and this peak can move up and down in time depending on the properties of the population. The 21 centimeter is very, so it's very science rich, but it also is very hard to model. There are many foregrounds and noises that one needs to overcome before we can get to the real signal. So here from a paper by Salim Zaroubi, this illustration shows all the layers that need to be peeled off on the way to the cosmological signal. The main noise is from our own galaxy, which produces synchrotron emission, and the amplitude of this emission is 5 orders of magnitude stronger than the cosmological signal. We also have point sources and radio frequency interference from any satellites or radio laptops and so on, which interfere, and therefore telescopes are placed in radio quiet zones. And also ionosphere blocks very low radio frequencies, so very high redshifts are inaccessible from the ground and one needs to go to space. However, people don't get discouraged. They're working very hard, and there are many telescopes that are trying to probe this radiation right now. There are few telescopes trying to measure fluctuations, and all of them publish upper limits. There are no detections yet in the power spectrum. In particular, WOFA, which is located mainly in Netherlands, but with fewer remote stations everywhere in Europe, including the UK, Ireland, Germany, Italy, I'm not sure, Poland, France. The main core is located in Netherlands, as I mentioned, and this experiment has published upper limits on the epoch of reionization fluctuations, so from redshifts around 10. The upper limit is still weak and it doesn't rule out any astrophysically motivated scenarios, but it was only derived from one night of data or very limited section of data, while they have a lot of data more in their pipeline. Low-far low-band, which looks at the epoch of cosmic dawn around redshift 20, also published upper limits just a month ago. So again, these upper limits are based on very limited chunk of data, and they are processing more data. It's very difficult to process it because one needs to take out all the radio sources, point sources that contaminate the signal, and also account for various systematic errors, which takes a lot of processing time. Other experiments are JMRT in India and MWA in Australia that published upper limits. So again, there are no detections in the power spectrum yet. And future is actually very promising. There are two two experiments that are promised to map fluctuations during cosmic dawn and reionization. Square kilometer array, here you see an artist impression. It will be located in Australia and will probe fluctuations down to redshift 25 or even 27, constraining astrophysical parameters. And the hydrogen epoch of reionization array, it's already under construction in South Africa. So I just visited a week ago the SK headquarters, which are located in Manchester. It seems that the experiment is getting up to speed. This is an image of the antenna that they are going to use to detect the cosmic dawn signal. And this is a test array located close to Cambridge. Meteor Radio Observatory, they are testing the antennas, even though the radio frequency interference is really bad in Cambridge. But the antennas exist and are under tests now. It's an international experiment, and there are 12 countries now contributing. France just joined recently. Hera is also under construction. The antennas are already in the field. This is a small part of the array, but they are taking data already. And they are now testing new feeds that will probe the epoch of primordial star formation. Original test goal of Hera was to probe reionization, but they got additional funding to extend the array to epoch of cosmic dawn and probe the heating fluctuations. So SKA and Hera have very different approaches to foreground mitigation, and it's really good to have both of them to verify future detections when they are there. Global signal experiments, there are also a few of them. These are just typical examples, the main examples. And as I mentioned, the big thing is this detection that is claimed from redshift 20 to 15. It is way off scale from all our models that I described. The models go as low as minus 250 millikelvin, bounded by the just gas cooling down through adiabatic expansion of the universe, while the detected signature is twice as deep. I will talk more about it at the end of my talk. Other than that, than this detection, there are upper limits again at lower redshifts. SARASII, which is the spherical antenna, very interesting design, has published upper limits has published the residuals, the noise at the level of 11 millikelvin, which is much lower than some of our models. So based on these low residuals, we were able to reject some of the astrophysical scenarios. EDGES High-Band, which is a precursor of the low-band antenna, it's just a very similar antenna, this antenna here, but tuned to a higher frequency range and probing redshifts around 6 to 15. They also have published very low residuals, around 17 millikelvin, and also rejecting some of our scenarios. And LIDA is another experiment, but it's an interferometric array which is used as a global signal experiment to probe global signal from redshift 20. It has published upper limits of 890 millikelvin, so it's still too large to constrain any astrophysical scenarios. And Sky High's upper limit is 1 Kelvin, sorry, there is a typo. But they both are looking at the epoch of cosmic dawn and first star formation. So now I want to focus on the epoch of reionization and show you some constraints that we have from the existing data. So this experiment, SARASII, is a spherical antenna that I just showed you earlier. And what we did, we sent them 264 different scenarios from the ensemble that I just showed, these models, and asked them to propagate this model through their pipeline and see if some of them are rejected. So this antenna has sensitivity to the entire redshift range from 6 to 34, but it's optimized in at the epoch of reionization, looking at the redshifts between 6 and 12. And here you can see how our signals propagate through the pipeline, and the sensitivity is much stronger at lower redshifts. This just shows the residuals, which are really small. So this team, the antenna is located in Himalaya, and they process 63 hours of data. And that's the result of their analysis. They managed to reject few of our models to a very high accuracy, so to a very high confidence level above 5 sigma. So some 10% of the models that we sent to them were rejected by the data. And though these models have two things in common, they either have very deep absorption feature, meaning that cosmic heating wasn't efficient, or a very abrupt reionization, meaning that reionization happened suddenly. Between redshift 6 and 12. So these scenarios are ruled out by this data. Then we send these models also to the EDGES team. EDGES High-Band antenna measures the signal between 6.5 to 15 or 90 to 190 megahertz. And the EDGES team had 240 hours of data. They rejected more models also to very high significance, but these models were from the same class with a very deep absorption and sharp reionization. So these two experiments showed the were consistent in that they disfavor cold gas and the fast reionization. The next step was to go broader and probe more models and come up with more quantitative constraints on the astrophysics of the early universe. We ran this code on a supercomputer in Harvard, or I mean Odyssey cluster at Harvard, creating a huge bank of models and used them to probe the parameter space of 7 different astrophysical parameters, which span star formation, history, heating, and epoch of reionization. So we created a tool that is based on neural networks, and the tool takes these astrophysical parameters and returns a smooth global signal. And it runs very fast. Our original simulations take few hours to run. It's fast, but it's still not enough if you want to do a Monte Carlo or probe the entire parameter space. This tool runs very less than a second and produces a smooth signal, which is very important because the experiments are really sensitive to sharp features in the signal. So using this tool, we were able to discriminate across the entire astrophysical parameter space that we probed. Here I show you the likelihood analysis of 6 million models produced with this tool. Bright regions are shown regions disfavored by data, and dark regions are still allowed by data. There are many parameters, and I don't expect you to memorize all, but some of the important ones are the minimal mass of star-forming halos, which tells us when first stars formed and in what kind of halos and through what kind of processes. There is star formation efficiency, F star here, which tells us what was the efficiency of first halos in forming stars. Fx is heating efficiency of sources, which tells us how much brighter were first X-ray binaries compared to what we see today. Tau is the CMB optical depth, and then we also probed the minimal frequency of X-ray photon, which effectively tells us what is the hardness of X-ray spectrum. And you see that amazingly, the EDGES High-Band data can discriminate across all this parameter space. In particular, it disfavors low X-ray heating efficiency, so we do need some amount of feedback of X-ray heating. It also rejects star formation in heavy halos only, meaning that we do need some small mass halos of around 10 to the 8 solar masses or lighter to explain the fact that the signal is not within their band. And there is also some sensitivity to the spectrum of X-ray photons, and that's very interesting also, because as you saw, the just change in the spectrum has a strong impact on X-ray heating. And there is some sensitivity to optical depth, but EDGES rejects very high optical depth above about 8%, but it's still much weaker than what Planck can do. Next, we know that the epoch of reionization starts being constrained by Planck, for example, through the total CMB optical depth, and also by high redshift quasars, which through their absorption wing profiles can tell us what was the neutral fraction at that time. So the few quasars at redshifts above 7, which we used, and this diagram here shows the probability distribution of neutral fraction at high redshifts. And it's still very broad, but starts being as constraining as Planck data in terms of reionization history. So using these external constraints, we could put priors on the minimal mass of star-forming halos. Optical depth is very strongly constrained, but there is also a little bit of sensitivity to X-ray physics, because X-rays do ionize gas very mildly, to few percent, and we can see it in this 1D probability distribution function. So putting together EDGES high-band data and also external constraints from quasars, we can actually discriminate along the entire parameter space that we studied, with some parameters still driven by EDGES data, in particular X-ray heating efficiency, the spectral energy distribution, and star formation. And now, how much time do we have still? The infinity. Okay. So this news, as I mentioned, came earlier this year in February, and it was shocking for the entire community, because this study that we did was just appeared a few months before the EDGES signal, and we saw that there is a fundamental minimum to the models. They cannot go deeper than the absorption in the just expanding cold universe, not heated by anything. So there is a lower limit to the signal. And EDGES has shown a very deep absorption feature at redshift around 17. Twice as deep as our models predict. And this feature is also very narrow, which is hard to explain. Some of our models do give such narrow signals, but then they are very shallow, because this means that we need to start forming stars, couple the spin temperature to the temperature of the gas early on, but then start heating up the gas almost right after that to ensure that the width of the signal is very narrow. So in this case, the signal doesn't go deep at all. So it is still a mystery. It's been almost a year, and we still don't know how to explain this deep absorption. This on the right-hand side, you see a plot from the Nature paper. This is the data that they took. It has information about the galaxy and everything else, foregrounds. Then they subtract foregrounds only, and they show that the residuals are pretty high, 87 millikelvin. And when they subtract residuals and the signal, so foreground model and the signal, which they model in this way, the residuals drop and are much smaller. So this means that the data has something else in addition to the foreground model. And this signal was their best fit model.
What they observed?
Sorry?
What's the observations? Kind of sky from different colored lines and so on?
Right. So the observation is they took during 2 years the brightness of the sky in the frequency range between what was it? I forgot. 50 to 100 megahertz roughly. So this is just a radio emission from the entire sky, which it's a wide. I forgot exactly what's the angle, but it sees half of the sky, roughly. So we don't expect fluctuations from cosmology in this. We do expect the galaxy to fluctuate, and in particular, this experiment just stares up, so the galaxy drifts across the field of view, and they do see the dependence of the signal on where the galaxy is. Sometimes the brightness temperature is up, sometimes it's down, but at any time they can extract the signal at roughly the same amplitude. So in particular, this table from their paper shows the derived best fit profile depending on the different binning of the data, on the time, sidereal time when the data was taken, and they always manage to reconstruct this, or to extract a similar profile. They also did many tests of hardware, and all these different colors that they show here correspond to different modifications of the instrument itself. In particular, they rotated it, they changed the ground plane, they made another copy of this instrument, and they always manage to extract the same signal. So it seems to be something on the sky that doesn't scale with the brightness temperature of the galaxy, and this led them to make such a claim, but they still themselves are open for possibilities that it's a foreground or something else. Also residuals, if you plot them as a function of integration time, with just foreground subtracted, at some point they stagnate and saturate, stop decreasing as expected, while with the astrophysical, with this cosmological model subtracted, the residuals keep dropping. So, it seems it's intriguing. If the signal is real, then as I said, it's impossible to explain its amplitude in terms of astrophysics, and we need something else outside of the full parameter range that we explored, which describes standard astrophysics. And in particular, there are two ways to explain it, either to boost background in addition to the CMB at something else at the Rayleigh's tail of the background radiation, or decrease gas temperature even more than just an adiabatically expanding universe. Both solutions are anomalous and are kind of extreme. If we just try to constrain astrophysics using the redshift of where the signal is located, sorry, then we can constrain the mass of first star-forming halos to be around 10 to the 8, because we would know that Lyman alpha coupling happened around redshift 21, and we also would know when X-ray heating started around redshift 17, so a first population of X-ray binaries formed. So these are two examples of solutions to how to explain the deep EDGES absorption. As I said, both solutions are anomalous and radical, and they are not part of our standard astrophysics. So first one is if you add extra radio background, then there is a stronger background from which neutral hydrogen can absorb. And this can lead to this very deep absorption. And I should note that actually excess radio background in the CMB low frequency tail was actually observed by two telescopes right now, Arcade and LWA. But we still don't know if this observation is actually cosmological or if it can be explained by the galactic emission. And the other type of solution, if dark matter actually interacts with gas and drains some energy from the gas through scattering processes. In this case, we can get such a deep absorption, but these theories are very strongly constrained, and only a few % of dark matter can actually scatter. And even if they scatter, they would have a tiny electric charge, 10 to the -6 of normal electron charge. People also discuss modification of thermal history if gas starts cooling down earlier than in standard theories. So if thermal decoupling from the CMB radiation happens at earlier times, then it would cool down to colder temperatures than we normally expect. Yeah, it's all intriguing. Actually, if fluctuations in cosmic micro in 21 centimeter signal are boosted in accordance with the observed feature, then they would be within the range of LOFAR or HERA. So we might see confirmation soon, or if LOFAR doesn't see these strong fluctuations, we would know that something is wrong. So I did some study where we took dark matter scattering models and varied also astrophysical parameters, coming up with thousands of these models, and many of them do fit EDGES, but again, these models are heavily constrained. And also, if we add extra radio background, there's a few examples from the paper in preparation. We would also expect very strong fluctuations in 21 centimeter signal within the range of LOFAR. So a bit of on confirmations. EDGES team, as I said, they are themselves open-minded, and what they are trying to do is to conduct more tests with existing instruments, but they also deployed another antenna in the intermediate frequency range. And they actually see the same signal with their mid antenna. Here there is an example of the test where they combine the data from low band and the intermediate band antenna, and they show that they extract the same feature. And if you're interested, they have a long list of notes, memos, very well annotated and very thoroughly written with all the tests that they're conducting. SARASII antenna, which we used in the high band to constrain astrophysical parameters, has evolved a conical dipole antenna, which is optimized in the redshift range between around 20, and they're in progress to try to verify the signal. They took some data in September, and because this experiment is in Himalaya now, it's not the season. But they constructed it right after EDGES discovery, so it's a very new model, and I imagine they need to conduct some tests to verify its performance. Another experiment, LIDA, is also taking data, and that's me helping them to calibrate the instrument. And there are very strong systematics, most likely due to foregrounds, due to the ground plane and interaction with the surrounding. And this systematics are on the scale of few Kelvin, so I'm not sure if we will be able to verify just the signal with this data. But this experiment is also located in California. There are very strong radio frequency interference that became worse in the past years, digital antenna, and there are also airplanes in the sky that contaminate the signal. So LOFAR, actually, as I mentioned, if the fluctuations are boosted accordingly, and we do expect them if the signal is real, then LOFAR will actually be sensitive to these fluctuations. And they got 1,000 hours just to probe and try to confirm or disprove EDGES signal. They are taking data, and it's a very hard task to process this data. If the signal is as strong, then also SK will actually be sensitive. SK1 will be good enough to do imaging, which in the standard case scenario would not be possible until SK phase 2. So if it's real, then it's great news for observers, actually. And I'd like to conclude. So I showed you, I hopefully convinced you that this is the most exciting time to do 21 centimeter cosmology. We have first constraints from our high-band antennas probing epoch of reionization, and they complement all other constraints on epoch of reionization that we have from quasars and the CMB. We also have first ever detection claimed from redshift 17, which probes the formation of first stars and the X-ray binaries. And the observational community is working really hard to try to confirm or disprove the signal. And right now we don't have a good theory to explain it in the standard astrophysical scenarios. Thank you very much for attention.
So, thank you, Anastasia, for this very nice talk and overview of this very puzzling detection. The podium is open for questions. And let me turn on the light. Matthias, wait. I know you can shout to it.
Yeah, I was puzzled at your power spectra. You had at least one slide where you saw the power spectrum at k equals 0.03. And the power was very strong and fluctuating very strongly. And I was wondering, how do I understand that you get so much structure and so much dynamics in that structure at a scale of about 50 to 60 megaparsecs?
Which slide are you referring to?
Rather early.
Too much light.
I think we're getting no.
Oh, I see. This one?
Yes, exactly. Bottom right, yes.
So 0.3, you mean the green one? Well, there are things happening.
0.03 even. I mean, that's a scale of about 50 to 60 megaparsecs, right?
Right, but that's in millikelvin squared, right? So you do, that's the structure you have, and it depends on the astrophysics as well. This is not, so this reflects the X-ray fluctuations because they actually do go to so large scales. They go to a few hundred megaparsecs, up to 1,000 megaparsecs from the X-ray binaries. Yeah, if you, so this is a relation between mean free path and the energy. Sorry, it's cut here. It's the power of 3. So if you have a very energetic photons of 2 keV, 3 keV, they even redshift out. They don't get absorbed at all. Very energetic photons around 1 keV travel 1,000 megaparsecs, co-moving megaparsecs, and do affect large volumes.
All right, I wasn't aware of that. How does that compare to the horizon size at these redshifts?
So few keV, they're much larger than the horizon side. I don't remember the number, but they never get absorbed because this mean free path is larger than the horizon.
All right, okay.
I think the horizon corresponds to roughly 2 keV photons. Mm-hmm. All the rest it just redshifts away and contributes to X-ray background.
All right.
Yes. Next question, Sasha Honi.
So I had a question about the shape of the EDGES profile. I have the impression, if I try to think about cosmic variance as well, that actually nothing what you discussed can explain why there's such an extremely abrupt transition from 16 to 15 in redshift. I have the impression all of the profiles that you showed based on models are actually much smoother, and they take time to settle to something.
Yes.
And so, is there any theory of in which direction to think to explain such a very abrupt transition from something which has enormous power to something that has no power at all?
That's a great question. Nobody knows. I can think about theory if you have few components and you have kind of heating floor, and then X-ray binaries actually start being more. So you would have something deeper, but you have a preheating, right? Then you would set the floor. But there are no good theories. It's one of the mysteries, this shape, and nobody knows why it's flat.
So, if I may, I had another question. When you say that you vary the astrophysics, I was wondering, are you changing, for example, the X-ray spectrum of all the X-ray binaries, or are you changing a probability density function of I mean, is each one of those curves having one set of astrophysical parameters, or actually should I look at these blue curves as something that has probability functions, and that actually some of your X-ray binaries are soft because they have higher accretion rates, and some of them are hard because they're not? So I was wondering how to actually interpret these blue lines.
Right. Thanks for the question. So right now it's rather simple. We just change all properties of the entire population. It's not a probabilistic. It's just we say one curve has very soft photons, the other curve has only hard photons.
All right, next question, Matthias.
You mentioned that you did a principal component analysis in your 5-dimensional parameter space. And I was wondering, first of all, how different are the principal components? And in what direction do they point?
And
in what direction do they point?
So we did it on for the signal, to describe the signal, and we found that only 4 are needed to describe it.
Which one can you drop?
Sorry?
Which one can you drop?
Which one?
Which of these parameters can you drop?
So they're not exactly along these parameters, they're in the other space. But that's a great question, something I'm exploring now. As we see from these plots, some of the parameters are degenerate when it comes to the global signal. And our model predicts also power spectrum, so we need some of these parameters for the power spectrum. But for EDGES High-Band, just looking at reionization, for example, X-ray efficiency and star formation rate are partially degenerate. So in principle, we could substitute it by one parameter, a combination of heating and star formation, and that would be enough probably. But it's something we are exploring right now. That's a great question.
Let me know when you have it.
Sorry?
Let me know when you have it.
Okay.
So you didn't talk about it, but on the slide, when you discussed possible explanations, you had also something about gravitational interactions between dark matter and visible matter. Is that right?
Could you repeat?
Slide where you discussed possible explanations.
Right.
You had also something about gravitational interactions between.
So
can you say a few words about that?
Yes.
So there, the second point, baryon dark matter interactions via gravitational.
So this is a model that was brought out by Pierre Sekivi and Houston et al. And that's a case of ultralight axions where they form Bose-Einstein condensation on very large scales, and then they would gravitationally attract baryons and cool them down through gravitational interaction. It's not a very well motivated model. You would need a condensate on a universal scale, so a size of the universe. And it's interesting because it involves QCD axions, but it's hard to imagine Bose-Einstein condensation of the size of the universe.
And how does it explain then the data?
Because the condensate itself is very cold, and then baryons are cooled down through that. That's all I can tell. I didn't dedicate much attention because it's just...
Yes, Andreas Just has the next question.
So in your astrophysical heating processes, do you include the heating by AGNs? I mean, the AGN should have grown in that also at similar redshift, yeah, to get 1 billion solar masses at redshift 7 or something like that.
Right.
Is it included, the heating by AGN? Or
So we looked at that, and the AGN, the heating by AGN is subdominant to X-ray binaries as a population above redshift 6. So in this case, they're not relevant, but we did look into that, and we did compare. And what is interesting is that the AGN formation is at lower redshift, so you would have accelerated heating at lower times compared to X-ray binaries. Right now we have either X-ray binaries or AGN, and in principle AGN contribute to very late heating. In this set of models we didn't explore them because they're in general subdominant from what we found. But in principle we do need to include them together.
Let me, I think, ask a similar question. I mean, when you say AGN, you are referring to these supermassive black holes at relatively late redshifts. But in principle,
I mean, we have redshift 6 or 7, we have billion solar mass black holes.
yes, exactly. So,
Right.
exactly. So that is the question I would add. I mean, in principle, you can have these supermassive black holes or massive black holes forming much earlier from
Right.
supermassive stars. I mean, in principle, stellar evolution can accommodate stars that are worth a few 100,000 solar masses before the general relativistic instability sets in, and there are chances, very rare, but still, these objects could exist at a redshift of 20 or 17 or 15. Is that something that has not been looked at, right?
So we looked just taking a very simple approximation scaling AGN mass function with star formation rate weighted by the halo mass, one of the models of Furlaneto, and we looked into that, but not into other like direct collapse black holes or anything like that.
Yeah, this was my question, because they are very rare events, and I think the likelihood has been very recently rediscussed in the context of new simulations and models.
Right. In this case, we would have very strong fluctuations, but not rare. So power spectrum would be even stronger.
Yeah.
I meant to look into that. I just didn't have time.
Okay.
It's a very interesting question too, because you would see different signatures from direct collapse black holes versus growing cretin
exactly. Yeah.
black holes.
Spiky in the former case. Yes, third question. Matthias.
I was looking at this again, non-gravitational baryon dark matter interaction. So the model that Renan first came up with, I was wondering, how does that survive the CMP constraints?
Well, that's a
very
great.
tightly constrained.
That's a great question. Barely. I don't have a plot here, but only 1 or 2% can scatter, and the charge can only be milli-electron volt. So there's a very tiny parameter space that is still open. But there is.
It must be a very uncomfortable niche to live in.
Right. So it's very finely tuned if it's the case, and
Yeah. I agree with that.
so even more interesting, it would create a very strong baryon acoustic oscillations if this is true, because of this coupling and the relative velocity between dark matter and gas, and we looked into that actually. So this is a case of these large-scale velocity flows that I was talking to you earlier. They are supersonic at recombination, and they have a BAO scale imprinted in the velocity profile. And we know they exist from just linear extension of linear theory. The velocity field, as you can see here, has a baryon acoustic oscillation profile. And because in the scattering, the scattering is modulated by the velocity field. So through the scattering, you have BAOs imprinted in 21 centimeter signal in this case, and they would be very strong. So the amplitude of fluctuations would be strong, and the BAO pattern would be very strong. So that's kind of a smoking gun signature. It cannot be created through other mechanisms. So if LOFAR sees something like that, then it's unique.